Hello, everyone. This is Group 15 and our lab report number one for analysis of simple DC circuits. My name is Eric Osmundsen, Panther ID 6397663.
This is Joseph Mossman, Panther ID number 1592752.
Our course is EEL3110 Circuit Analysis and Lab. Date of experiment is February 2nd, and date submitted is February 3rd.
Our objective today will be to design, measure, and simulate a series of simple resistive circuits.
For activity one, we had the conditions of selecting a voltage supply between 2 volts and 6.2 volts. So I selected 5 volts and a resistor greater than or equal to 2.7 kilo ohms. We had to measure the following variables that you see in the table there and tabulate it. From the results, they were consistent with DC behavior with an open circuit. The resistor upstream of the open creates a voltage divider between the resistor itself and the open, and the voltage drop is proportional to each of the resistance with respect to the 5-volt supply. The resistance created by the open has a significantly higher voltage drop of 4.997 volts and then the 2.7 kilo ohm resistor of 1.349 millivolts. Because of the open, little to no current is actually passing through. We had 0.888 microamps, and the VBC and VDE has a voltage of 0 because there's no potential difference across the same node. VAD shows the voltage drop is approximately equal to 5 volts, so KVL still stands.
Activity number 2, we assigned V a value of 6.0 volts, R1 is 3.5 kilo ohms, and R2 is equal to 8.1 kilo ohms. And the values of VAB, VBC, VCD, VDE, VAD, I1, and I2 are as shown in this slide. These results are consistent with what we know about Ohm's law. Some voltage and amperage values are 0 because there is no closed path in the circuit that goes through R2.
For activity 3, we had three circuits with resistors in series, each with the condition as followed. For circuit A, we had the first resistor greater than the third resistor. For the second, the first resistor was less than the second resistor. And for the third, we had resistors being equal to each other. And the results are shown on the screen. The results were consistent with resistors in series. R equivalent is equal to R1 and R1 plus R2. For the 2 kilo ohm and 1 kilo ohm, we had 3 kilo ohms, 500 and 330. We had 830, and the 2 kilo ohms equal to 20 kilo ohm. When the resistors of the same value are in series, the equivalent resistance is just twice the value of each of the resistors.
For activity 4, V is given a value of 11.5 volts, R1 is assigned 8 kilo ohms, and R2 is 800 ohms. And VAB comes to 11.5 volts, I is 1.307 milliamps, and VAB over I is calculated at 8.799 times 10 to the 3 ohms. Section B, V is also 11.5 volts, R1 is equal to 300 ohms, R2 is equal to 3 kilo ohms, VAB comes to 11.5 volts, I is equal to 3.485 milliamps, and VAB over I is calculated at 3.3 times 10 to the third ohm. For C, V is again 11.5 amps, R1 is equal to 500 ohms, and R2 is given an identical value of 500 ohms. VAB comes to 11.5 volts, I is equal to 11.5 milliamps, and VAB over I is 1.0 times 10 to the 3 ohms. And with D, we use the same values for A, B, and C and determine I1, I2, VAC, and VCB. Now, for each of these examples, current is identical for each resistor, which is in accordance with Ohm's law.
For activity 5, we had 3 circuits with resistors in parallel. For the first circuit, circuit A, we had the first resistor greater than the second resistor. For second circuit, we had the first resistor being less than the second resistor. And for the third circuit, we had the resistors equal to each other. Results were consistent with resistors in parallel formula. For the 2 kilo ohm and the 1 kilo ohm, we had 66.7 ohms. For the 330 ohm and 500 ohm, we had 198.8. And for the 2 kilo ohm resistors, we had a 5 kilo ohm. The equivalent parallel resistance will always be less than the resistance of the smallest value. And if the resistors of the same ohmic value are in parallel, then the equivalent resistors will be half the value of each resistor.
Activity 6, for A, B, C, and D, we assign values to R1 and R2 and V. And from there, we measure VAB, I, and calculate VAB over I. And the results are as shown here on the slide. For section D, beg your pardon, for section D, we use the same data for A, B, and C and use it to calculate these other values here, I1, I2, VDE, VFG, VAF, VAD, and VFC as shown. And once again, these results are consistent with the equations in the text.
So for our discussion and conclusions, after completing the lab activities, we learned how to design, measure, and simulate simple resistive circuits. All circuits behaved in accordance with what was expected from Ohm's law, KVL, KCL, and short and open circuits. Our biggest difficulty was that this was our first lab together, so getting organized and used to personal schedules was kind of tricky. We were missing a group member, and we had no MyDAC to play with hardware. Experience gained, familiarity and comfort in using NI multisim software. Thank you.